Hello viewers, welcome to my channel. Today I am going to discuss electromagnetic induction. So let us start. We first start with magnetic field lines. Now we know them. Let's consider these magnetic field lines. I need the pen to deep. So now we consider this picture. Here the magnetic field lines of a bar magnet. Clearly the magnetic field lines originate from North Pole and it ends in South Pole. And inside the bar magnet, it goes from South Pole to North Pole. This is the direction of the magnetic field line for a bar magnet. Okay. Now we consider this picture. Here, two poles of separate magnet. First, complete these two magnet. This is a separate magnet, and this also a separate magnet. Okay. Then the magnetic field lines will look like this. So again here the magnetic field lines originates from North Pole and it ends in South Pole. But for the separate two magnets, the magnetic field lines again originate from North Pole and it goes to the South Pole. This is the picture of magnetic field lines due to a bar magnet. Now these field lines have no endpoints. Okay, these field lines have no endpoints. The field lines are closed. This has a physical significance we will read later in Gauss law of magnetic induction, where we will read that magnetic monopole does not exist. There is a some implication here. So field lines have no endpoints. These imply the magnetic monopole does not exist. Magnetic monopole does not exist. Okay. Now another one thing we have to consider from this magnetic field lines: the more close the magnetic field lines, the more strength here. We consider this picture. Here in the near the pole, the magnetic field lines are more closed, so more strength of the field is here. And as we away from the magnetic poles, we see less field strength in this region. Here in this region. Okay. So we know the magnetic field lines. Now we move on to the next slide. Now we will study here magnetic flux. What is a flux? Okay, so first draw some magnetic field lines. It's not so good, but I am trying to say that what is a flux? These are few field lines. Now we consider a unit area perpendicular to these field lines. Okay, this is unit area perpendicular to this field line. This area we say this is a unit area. Then this unit area encloses how many field lines? 4. Here for example say 4. Then this is the magnetic flux due passing through this surface. Okay, the concept is like this. If there are field lines, go we take a unit area cross section perpendicular to the field lines, then number of field lines passing through this cross section is the magnetic flux. Okay, now we generalize this concept here. Here we have taken this surface element, is surface area ds. Okay, and this normal is the direction of the surface area vector ds. If the magnetic field lines is not parallel to the surface area vector ds, it makes angle theta with the surface area vector ds. then its flux will be the projection of the magnetic field to along the surface area vector. Okay, and here we write the magnetic flux d phi b equals to b dot ds. This dot product implies the projection of b along ds. Okay, and there is a angle theta between surface area vector and this magnetic field. So we write the magnetic flux, elementary magnetic flux d phi b equal to b ds cos theta. Right. Now to get the total flux enclosed by this surface, we will integrate this b ds cos theta and we find b dot ds. Okay, this is the formula to find total magnetic flux enclosed by the surface. Okay, and we get phi b equals to bs simply. Now here is another pictorial depiction that the first in this first picture, the magnetic field lines are not parallel to the surface area vector. It makes angle theta with the surface area vector, so the flux is phi b bs cos theta. But in this case the magnetic field lines b is parallel to the surface area vector, and so we get magnetic flux phi b equals to bs. So we get the flux. Now Gauss's law for magnetism. Here it reads b dot closed surface integral b dot ds equals to 0. We read in electric Gauss's law, what b dot ds equals to 1 by epsilon times charge enclosed. That the for magnetism the magnetic monopole does not exist. So whenever a surface encloses, the magnetic dipole is present there. Okay, north and south both are present there. So if north and south both are present there, then the magnetic charge, what is equivalent to the electric charge in electrostatics, the magnetic charge is total charge is 0 here. So as the total magnetic charge is 0, so b dot ds is equals to 0. This is the Gauss's law for magnetism. Now this law tells us that magnetic monopole does not exist. So we move further. Now come to the Faraday's law. First consider this picture. Here a bar magnet is moving towards or away from a closed circuit. Now when this bar magnet approaching this closed circuit, you see this coil, a current flows and it is measured with this ammeter. How? Because when the bar magnet approaches to the closed circuit, this circuit, the magnetic flux changes, right? This magnetic flux induces an EMF in this circuit, and this induced EMF makes induced current, and it is measured with the ammeter. Now this induced voltage small e is equals to negative sign d phi b dt. D phi b dt, what is it? The phi b is the magnetic flux and d phi b dt is time rate of change of this magnetic flux. If the stationary flux present, then there is no induced EMF, then it will be 0, right? Now statement: the induced EMF in a closed loop equals the negative of the time rate of change of magnetic flux through the loop. This is the Faraday's law, and this is the mathematical form: E equals to negative sign d phi b dt. Now we will study details this negative sign in Lenz's law, right? Now come here, Lenz's law. What it says, that this bar magnet is approaching towards this coil, and what is the current direction of the current when it is approaching the coil? Its direction is this, and when it is leaving, it is moving away from the coil, its direction reverses, right? So the direction of any magnetic induction effect is such as to oppose the cause of the effect. Now the induced EMF is caused due to this approached magnet, but this induced EMF makes induced current, and this current opposes the movement of this magnet. Okay, this is Lenz's law. So this negative sign is due to the Lenz's law. Now study in detail in Lenz's law. It is a solenoid. When a bar magnet is placed very much distance, it is a very greater distance, it has no effect on this solenoid, right? Now when it comes close to this solenoid, you see induced current will flow, thereby create a induced magnetization in the solenoid. And which pole it will create to the nearest end? It will create the same pole. Why same pole? It will oppose the magnetic flux, change of magnetic flux. So it is same pole. Now when this bar magnet is moving away from this solenoid, it will make here south pole. It is very interesting. So explains the solenoid diagram, explains Lenz's law very clearly. Now what will happen if we increase current in loop 1? There is two loops, number 1 and number 2, number 1 and number 2, these two loops, and current I1 is flowing. If this current is steadily flowing, then there is no change in this loop. But if we increase this current I1 with respect to time, it is gradually increasing, then there will be an induced current in this loop, and the direction will also be opposite to the flowing current in this loop, and for this reason they will attract each other. Okay, so they will come close to each other. Now we will study motional EMF, electromotive force. So first we see this picture. Here a rod of length L is placed in a magnetic field. These are the direction of the magnetic field. So the field lines are entering the paper, right? So we represent it by cross. And this piece of metal rod L is moving with velocity v in this direction, with velocity v. Then magnetic force on the electrons in this metal is E equals Fm. Force due to this magnetic field Fm equals to minus sign E v cross b, and the sign of v cross b, the direction of v cross b, v is along this direction and b is along, let's say for example we cannot represent 3D exactly, in this direction, then v cross b, this direction will be here, right? V cross b, the direction will be perpendicular to the plane containing v and b and in right angle. So this direction will be like, so in this metal rod the magnetic force will apply to the electron, thereby they are moving in this direction and the holes will be moved in this direction. So clearly there is a difference in charge. There will be a induced potential due to this accumulation of charge on the ends, right? Now this will create a electric field inside this metal, and this electric force will be E times E. Okay, this electric field is the induced electric field due to the movement of this metallic rod in the magnetic field, and the force is minus E v cross b. Now the magnitude of this force is EVB. This force will balance the electric force. So the left hand side is the electric force and the right hand side is the magnetic force on the charges. These two will balance, and this balance will create motional electromotive force. Now E shown EVB, so the electric field or electric force E equals to V multiply B, and the potential difference delta V, the potential difference between these 2 points, delta V equals to E into L equals to BLV. So the motional EMF delta V equals to BLV, right? So motional EMF delta V equals to BLV. Now the motional electromotive force in a U-shaped loop. This is a U-shaped loop in a magnetic field. The lines of the magnetic field is represented by this cross. So these magnetic field lines are entering into the paper, and there is a loop, U-shaped loop, and there is a conducting rod of length to which can slide throughout this loop. Now the length rod L is moving with velocity v in this magnetic field. Then what will happen? It will make a closed circuit here, this rod. Okay. Then the motional EMF E is VBL, we derived earlier. So here a motional current will appear due to the motional EMF in this loop along this direction. This current is I equals to E by R. R is the resistance of this loop, the external resistance. And if we put E equals to BVL, then the induced motional current is BVL by R. Okay. So we will stop here for this part. Hope you enjoyed. Thank. Okay. Now there is motional EMF induced in a rotating bar. This bar of length L OP is rotating with angular velocity omega in this magnetic field, right? In this magnetic field, the length of the conducting rod is L. Now we first take very small element dr, and this dr is moving with linear velocity v at a distance r from the origin O. Now we will calculate the motional EMF due to this dr, then we will integrate this length OP in the expression for dr. So dE, the elementary motional EMF, is V dr. V is the velocity, V is the linear velocity here of this element dr, right? Now we replace V by R omega, so B R omega dr. Now to find the total motional EMF, we integrate this quantity for the full length 0 to L, because OP has length L. So we get E equals to 0 to L dE, 0 to L V R omega dr. Now this omega constant angular velocity, this magnetic field is constant. So B and omega comes out. What is left? Integration 0 to L R dr. Integration 0 to L R dr. And this integration is R square by 2. R square by 2. So if we put the limit is L square by 2. So we get the expression E equals to B omega L square by 2. Now this motional EMF is the potential difference between the 2 point P and O of this rod of length L. So Vp minus Vo equals to B omega L square by 2. So thank you for watching. We will come with the next part of this series.